Welcome to the second part of this tutorial. Just in case if you skipped the first video, my name is Evgenii or Zhenya Vinogradov, whatever first name is easier for you. You do not strictly need to know the content of the first video to understand the material presented in this part, but I still recommend to watch the introduction. Okay. Probably all of you have seen air traffic controllers in movies. But actually, what are they doing? This video shows how the air traffic was affected by the pandemic. But it is not why I am showing this for. The video demonstrates how the airspace is managed. There is a global picture, but in fact, it consists of national airspaces. And national areas are divided into sectors. In each sector, a number of planes is managed by a human air controller. This person has information of the flight plans, current status, type of aircraft, and many other things. Based on this, he or she is routing them, we may say, manually. Well, as we see in movies, they are always talking to the pilots and with each other to coordinate the traffic. Of course, movies are not always accurate. Do you remember how shocked those people by the word conflict appearing on the screen? But it's actually their routine. Their job is to manage the conflicts. Here you can see a real air traffic control center. It looks much more relaxed than in movies, right? And completely drama-free. Unfortunately, it's not always the case. In July 2002, a Russian passenger jet and a cargo jet collided above the Lake Constance in Germany. Over 70 people were killed. The investigation indicated multiple conflict management problems, including procedure ambiguities and possible human factors. 2 years later, Peter Nielsen, who was the air controller that night, was murdered in an act of revenge by Vitaly Kaloyev, who lost his wife and 2 children in the accident. This story is shown in the movie called Aftermath. You may have a look. Apart from the movie, the accident resulted in multiple changes and clarifications in the conflict management procedures and controllers' responsibilities. It was reflected in the international regulations and legal documents. The current version of these regulations is from 2005. 2005. Sadly, but the conflict management rules are shaped by accidents. That is why the procedures are quite well thought through. In the first stage of drone technology evolution, we will probably have to follow similar rules. Well, of course, we have to adapt them to the new circumstance, but still, that is important. Another argument is that we must ensure compatibility and coexistence of these two systems, ATM and UTM. Manned and unmanned aviation will have to share the common airspace, and it's logical if rules are similar or at least transparent for all involved actors. Let's see what happens with conflict management. It is the core of ATM, air traffic management. Of course, conflict management is not the only part of it, but it's the heart of it, and for this tutorial I have to narrow down the scope, and I took the most important part. Okay. Another issue that I'm going to cover in this video is UAV traffic management, or UTM. So additionally, I will show how ATM and UTM should communicate and how they are related. I know you were waiting for this moment and finally it's arriving. I'm going to switch to the slides. We will start by clarifying some critical terminology. First, let's define what conflict management is. Conflict management is the process of ensuring that aerial vehicles do not physically collide. This definition is taken from the document written by ICAO, International Civil Aviation Organization, for manned aviation, surely. But the drone community also uses this definition. And, well, I must underline that there is a common mistake. Conflict management is often confused with collision avoidance. Remember that conflict management is more general, and collision avoidance is just a part of it. Conflict management is also often confused with sense and avoid technology, but again, conflict management is a process, not a technology. Conflict management consists of 3 independent layers that together ensure the minimization of collision probability. The procedures must be performed to limit, to an acceptable level, the risk of collision between the aircrafts. Each layer measures aimed to reduce the need to apply the next layer procedures to an appropriate level. In other words, the second and third layers will only be activated if the higher layer does not work. Even though the layers are explicitly separated, it is recognized that the continuum exists from the earliest planning of the flight to the latest avoidance maneuver. Conflict management usually consists of strategic and tactical deconfliction. Strategic deconfliction, or mission scheduling, performed at the first layer of conflict management. It is basically the airspace organization and management, or in other words, flight planning. The performed tasks are first demand and capacity balancing and second traffic synchronization. Strategic actions typically occur before departure, however, they are not limited to pre-departure, especially in the case of longer duration flights. The second and third levels are collectively called tactical deconfliction. Let's start with level 2, separation provision. More popularly, it's known as remaining well clear. Separation provision keeps aircraft away from a hazard by an appropriate separation minimum. It is an iterative process consisting of several steps. First, the conflict should be detected. The detection is performed based on the current position of aircraft and the projected trajectories, for instance. Next, a solution is formulated based on the hazard nature. Well, indeed, the conflict horizon is different for collision with a mountain, building, or other aircraft, right? Next, new trajectories should be checked to ensure that they're free from other conflicts or new conflicts. Then you have to implement the solution. Well, it's just trajectory modification. And of course, you should check that the solution is implemented. Collision avoidance is the last hope to avoid an accident. I was trying to find formal but simple definition of collision avoidance, but I think the clearest one was given by a pilot, and he told that, well, you understand that it's collision avoidance maneuver when the pilot does something like, oh my god, and instinctively does something to prevent the accident. Voila. But, okay, the more formal definition probably still needed, and it is, collision avoidance is the third layer of conflict management. It must activate when the separation mode has been compromised. Collision avoidance is the last resort to prevent an accident. Okay, what is the role of wireless technology in all this? Well, we must design new or adopt existing technologies for supporting these operations. Note that we cannot exploit the same technologies as used in manned aviation since we risk compromising people's safety. For example, ADS-B. It's probably the most popular technology for exchanging the coordinates between air traffic controllers, planes, and other actors of that kind. Let's imagine that we have thousands of drones which are doing the same. It will result in frequency spectrum congestion. We will not receive a lot of important messages, and, well, the safety will drop a lot. We cannot do that in this, that means that we cannot use the same technologies, but we still can rely on Wi-Fi and 4G. Read this paper for a short overview on how we can accommodate the UAV conflict management needs. It also contains the description of conflict management and other things. If you don't want to rewatch the tutorial, just read the paper. Many things are told there. Let's start with the airspace organization. First of all, the manned aircraft have been there for a while. Drones are becoming common, but still they are new agents in our airspace. We have to somehow include them into the currently functioning air traffic management systems. This figure shows a typical approach to do that. Do not pay attention to the numbers, since they differ from country to country. What matters here is the idea that the common airspace should be divided into several slices or echelons. Logically, drones will occupy much lower altitudes than manned aircraft. The aim is to minimize the usage of the same volumes by drones and manned planes. The airspace organization schemes are typically published by national aviation agencies, so I just advise you to check the website of your, of the one in your country. What is the role of air traffic controller in conflict management? Their main goal is to keep aircraft separated. It is basically ensuring the well-clear separation. Consequently, they mostly perform the operations of the level 2. So they detect the conflict. Based on the gathered data, they resolve the conflict. How do you do that? Of course, you do not want the aircraft continuously change their trajectories, altitudes, etc. So the solutions must be as simple as possible and include as few modifications as possible. Then the air traffic controllers verify the solution implementation done by the pilots. And how do they do that? Just by talking and by checking other means like radars and other things. Okay, so they verify the solution implementation. That's it. In future UTM systems, these operations will have to be performed automatically, I would say. And, NASA, international European agencies, Russian and Chinese national agencies are designing UTM systems. For more details, I again refer you to this paper. In general, communication support of UTM systems is very important. I think our community should pay more attention to this domain and the use case. We need to exchange the coordinate between between drones, for instance. And we can do it through Wi-Fi or through LTE. Again, refer the paper. But we also need onboard cameras and radars, maybe, or other equipment to detect the conflict and coordinate its mitigation and not only be dependent on the communication itself. Okay, let's go back to conflict management. What can air traffic controllers do to change the trajectory? Actually, a set of actions is quite limited. Okay, you can hold. It's not commonly used because the airspace is huge and it's possible to use less invasive maneuvers, whatever. However, in busy areas like around large airports, it's relatively common. I guess many of you spend quite some time circling in the holding pattern preparing for landing. Well, at least I have. You also can modify the speed. Usually planes travel with the cruise speed optimized for the aircraft type, weight and altitude. But of course you can, up to some point, slow down or accelerate. If we're talking about drones, those first two actions are quite different because drones can hover and the range of speed is very large because it can go from hovering to actually pretty high speed. Both drones and manned airplanes can detour or shortcut. I don't know if it's needed. Well, for drones, actually, it's also not a bad idea because cruise speed, so there is a speed that is more optimal for energy than hovering. So that is a good option. Another rare maneuver for manned aviation is altitude change. It's not common because the altitude is an important factor for optimizing the fuel consumption. And you also avoid putting an additional mechanical stress when it's not strictly necessary. Planes are designed to move mostly horizontally. And, well, the altitude is changed only if there are other reasons to do that. For instance, you will have to do it soon in any case. For drones is slightly different. Drones have more degrees of freedom. As you can see, the action space is not that large for airplanes. If you want to make it more autonomous, it can be described by a relatively simple finite state machine model. On the other side, you can see, that drones have more degrees of freedom, more flexible, and the range of speed is higher, and, many things are more complex. And, on one hand, flexibility is good, but on the other hand, you have more degrees of freedom and more complexity. Especially if you're dealing with another aircraft. In case of airplanes, it's kind of easy to predict where the aircraft will appear in a few seconds. With drones, it's more complex. Another trick commonly used by the controllers is to group an aircraft by conflict. What does that mean? Let's imagine two airplanes moving to the same destination. At some point of the flight, there is a common waypoint, and let's imagine that the planes are approaching each other or approach this waypoint more or less in the same moment, at the same time. When this conflict is detected, the controller has to ensure that appropriate separation is there at the intersection, I mean. For instance, you can accelerate one and slow down the other aircraft. But the next step is actually very nice. If you line them up, the aircraft, and make them move in the same direction with the same speed to preserve the separation, then you can kind of relax. Because, first of all, the pairwise conflict management is super simple. It's trivial. But second, you actually can treat a few aircraft as one large aircraft. By this, you just reduce the number of conflicts and you simplify a lot your conflict management. Voila. So you just significantly reduce the number of agents in the air. I believe you can do this for drone application as well. Not for all of them, but I guess for some repetitive flight routes, like for patrolling, surveillance, and things of that kind, or especially for drone delivery. We can line up many drones delivering parcels to the same neighborhood, then move them together, and then at some point they can spread over the neighborhood. I think this is a good solution that will be more practical than the others. So In some papers, this idea is called as platooning. I think it makes sense. And I would like to say and pay your attention to this platooning idea, because we actually need good protocols, we need good wireless support for these platooning solutions. I already mentioned UTM. I think by now it's clear that if we are targeting hundreds or even thousands of drones in the air, we need those systems. To design a successful UTM system, we need to ensure the proper communication between ATM and UTM. It does not imply only data transfer, but some people claim that the whole philosophy should be the same. They motivated by the argument that manned aviation should have a priority. And I have to say, it sounds reasonable. Consequently, the new users of the airspace, namely drones, must not disturb the existing system. Indeed, we should limit the influence. However, ATM will anyway have to transform. The airspace will not be the same as before. That's why ATM also must align some services with UTM. Here you can see a simple UTM architecture and main agents involved in this. As you may guess, there is a lot of work to be done to ensure appropriate communication and coordination in a reliable and secure way. Summarizing the key ideas in a few phrases. Strategies for airspace organization and reservation will have to include drones as new agents. ATM is not enough anymore, and ATM also will have to align some services with UTM. These two systems should work together in future. If we want to ensure proper coexistence of these two systems, we should use similar design approaches, or at least we should use the same terminology for proper communication and service design. That's why I spent so much time explaining conflict management and its levels. Common language is the key. Let's look in the heart of the conflict management. The main goal is to keep drones separated from each other and from other objects around. Very practical question: how far the drones should be? This is a very important question for the communication systems too. It will define targeted coverage range, latency, and other performance metrics. Again, here we can try to rely on manned aviation background, their experience, and a century of exploitation experience. One of the ways to define this separation is based on time to collision. It's a straightforward approach, but maybe it's the only advantage. It does not work well with 3D separation. Well, it becomes too complex actually. As I mentioned earlier, the range of speeds is too large and it's not proportionate to the size of drones, so it becomes very difficult. Another very popular way is a virtual hockey puck around the aircraft. This approach is also simple. The question here is how large the well clear and collision avoidance cylinders should be. It's a trade-off, since large volumes will be prohibitive for wide-scale urban deployment, but small volumes will result in a very complex conflict management algorithms. This slide presents result of two nice papers. The authors analyzed characteristics of hundreds of drones and came up with these recommendations. Since the drones are more 3D creatures than the planes, then it makes sense to use two spheres instead of the hockey puck. I prepared a small demo. I did not prepare, but it will be done soon. Wait a second. Okay, done. Unfortunately, I did not find spherical balloon, but that is okay. So we have two spheres. One is larger than the other. This is well clear sphere, and inside I have another balloon with collision avoidance volume. I also have my drone. Let's imagine that inside there is not only the other balloon but another drone. And when we are flying, we yes, there was the second balloon. Unfortunately I ignored the physics, the pressure and stuff. So that's not what's going to happen in real life. In real life, only the first balloon would explode, and we would have to actually rely on the procedures of the second balloon, so of the second volume. Okay, not a very successful demo, but I think you got the meaning more or less. In this video, I explained conflict management and its levels. I shown the approaches for airspace organization. Moreover, I described what ATM and UTM systems should and will do. You saw the UTM architecture, and also you saw different approaches for defining the separation distance. I think that was quite a productive video. In the next part, I will describe the wireless technologies that are useful for conflict management and UTM. See you there!